wanted to make sure that we're recording this. I'll repeat some of the things we just said for purposes of the recording. Where we're at is we're looking at various technique factors. What factors determine the final image as far as the exposure technique? And the exposure technique consists of the time of exposure, the MA, the MAS, the KB, the filtration, and the last one we looked at was the target atomic number. If you remember, there we have the standard atomic number is atomic number Z is tungsten for CT, for radiography, for fluoroscopy, and now even a tungsten is starting to be used in digital mammographic units. But classically, the mammographic units were using molybdenum and or rhodium targets. But let's move on to the final of the parameters of interest, and that's distance. At what distance do you place the patient? And what happens if you change that distance? What does that control? So let's start in over there. Let's go to the big view. Okay, and we've been giving you these kinds of pictures up till now, where we plot the energy distribution of the emerging beam, the beam that's incident on the patient, and what is the number of photons at any particular energy level, the intensity of X-rays for any particular energy level. And you have these familiar looking curves. These are the Bremsstrahlung curves. They're continuous. They're polychromatic. We've talked about that a number of times. And what you see here is what happens as you change distance. And if you're at a short distance, in other words, very close to the source, you'll have a lot of X-ray photons. That's a no-brainer. The closer you are to a source, the more intense radiation is emitting from that source. But what happens if you go further away? Well, if you go further away, there'll be less and less radiation. And that's given by the yellow curve in this slide. And but what's to be noticed is what changes as you change the distance. The energy does not change. You started out with a particular Emax, you end up with the same Emax. Remember, the Emax is controlled by the voltage, and we are not changing the voltage. All we're changing is the distance here. Notice that we started out with a certain, at the zero energy, and you end up at zero energy. So it starts at zero and goes up to Emax in both cases, irrespective of the distance you're operating at. The difference is in the y-axis, the intensity of X-rays. How many photons do you have? And so in a quick statement, we say that as distance goes up, the beam quantity goes down. And why does that happen? Inverse square law. We talked about that earlier. Inverse square law. Inverse square law is the mathematical law that describes the variation of radiation intensity with distance, the very thing we're talking about. And then notice the patient dose. If you go further away, you're going to have fewer photons. Well, if you have fewer photons, there'll be less photons incident on the patient, and the patient dose will be less. There are other parameters that are involved in that calculation that also dictate lower patient dose. So in general, the further away you put the patient from the source, the further away or the higher the larger the SID, the source image distance, the lower the dose to the patient. What happens to the image effect? Well, remember we talked about the noise in a digital system? The noise depends on how many photons you have. But wait a minute. If you have fewer photons at the longer distance, then you're going to get more noise. Noise and photon number go in opposite directions. So if the intensity of X-rays goes down, the noise goes up. And if you're in a film modality, well, then if you have less radiation incident on the film because it's further away, then the density, how black it will get, will be less and less. And then the beam quality. Beam quality, remember, was a measure of penetration. It was a measure of how, what has happened to the energy. but nothing has happened to the energy in this case. So nothing happens to the beam quality. Nothing happens to the energy. Your Emax is the same. E effective is the same in both of these cases. So there's no change in penetrating ability. And if there's no change in penetrating ability, remember, penetration ability or energy determines contrast. And so if there's no difference in energies, there'll be no difference in contrast. Just what importance is this distance parameter? Well, let's go down the line. Here is on the slide. I've summarized a couple of them. I just mentioned noise. Noise goes as the photon number. And in fact, it goes inversely to the photon number. So that when you're changing distance, you will get a change in noise. If you go further away, you get more noise. If you come in closer, you get less noise, because noise is inversely determined by the number of photons. Now, if you're relatively far away and there's very few photons arriving at the image plate, well, now we have another problem. And the problem is that you would have to expose a long time to be able to gather enough photons so that the noise doesn't kill you. So if you go further away, there's less radiation that normally will give you more noise. But to overcome that noise, because you don't tolerate that noise, you have to then up the exposure time. And if you up the exposure time, then you are introducing the possibility of motion blur. And in digital systems like CT, you're going to increase the presence of image streak artifacts. The final point over here is magnification distortions. And when you go to a short SID, why would you want to go to short SID? Because you get more photons. You get more photons, you don't get as much noise. And your exposure times are short because you got more photons. Those are big reasons you would want a relatively short SID. But when you go to short SID, then you're going to have magnification distortions. In a later chapter, we're going to be talking about magnification distortions. You want to avoid distortions in your image. Just what form those distortions take, we'll cover when we get to the, that's actually in chapter 8. We'll be looking at that, okay? So distance, which controls number of photons, also controls noise, it controls exposure time, and it controls magnification distortions. In other words, distance is important here. And you have to come to a compromise in terms of what is your optimal distance. You don't want to make it too close because dose goes up. You don't want to make it too far because then noise goes up and motion blur goes up when you extend the time. In mammography, we operate at 65 centimeters. That's pretty much the universal SID, source image distance, for mammography. The universal SID is 100 centimeters in regular radiography, both film and digital. And one of the questions that often asked on the boards is, how come we do 100? 100 is optimal for radiography, but 65 is used for mammography. How come? And so what? Well, in mammography, we have very low outputs. There's not very many photons to work with. How come? Well, we work with low kV. Right there, you're going to get a less output. Okay, and we work with low atomic number targets like molybdenum and rhodium. Low atomic number targets we had concluded that the lower the Z, the less the output. There's when you have a low Z, that means that the nuclei have few protons. And if the nuclei have few protons, they don't attract electrons very efficiently. And remember, how do we get X-rays? By having high energy, high kinetic energy electrons deviated from their path as they approach various nuclei. But if the various nuclei have very low attractive power because they have few protons, positive charges attracting the incident electrons, you're not going to deviate them as much. You're not going to have as much energy and as much X-ray flux coming out. So we go to a shorter SID to make up for the fact that we have a relatively low output. And we go to that shorter distance because we don't want to have very long exposure times. Motion kills us. And as it is with these low outputs, we have relatively long exposure times as compared to a radiography. So that let me restate it another way. We would normally have very long exposure times in mammography because you have such a low output. Here's another reason why you have a low number of photons arriving at the image detector in mammography. Remember, you're dealing with low energies. Low energies means they're very easily absorbed in the patient. And that means relatively few photons coming out of the patient. Again, the problem of few photons arriving at the image plate. So putting all of that together, you start out with low X-ray outputs, and then to boot, you have very little penetration out to the image plate. We have to go to a shorter distance, even though that produces more magnification distortions, but at least we have, we minimize the motion problem, okay? And the motion comes about because of the otherwise long exposure time. Okay, moving on. Now, here's another variation on the universal SID. We mentioned that standard radiography is done at 100 centimeters, but upright chest radiography is done at 180 centimeters, 72 inches. And again, how come? Why do we use chest at these very long distances compared to everything else? And there we're looking at the fact that if you go to a larger SID, then you get less magnification distortions. Well, we are particularly interested in minimizing distortions in a chest film. And going to the longer distance allows us or minimizes the magnification problems. Okay, it also gives us true dimensions where your dimensions are actually real dimensions. You know, they correspond to the dimensions seen in the image correspond in a set manner to the image to the dimensions in the patient. Okay, so those are two good reasons why we want to go to a long SID, and we can get away with it in upright chest because you're going through a chest. A chest is mainly lungs, which is mainly air. So there's a lot of penetration available. And if more penetration is available, that means you're delivering more photons to the image plate so that you do have a relatively high amount of photons arriving at the image plate. Also, we operated at high KVs for chest films. Well, high KVs give us even better penetration. So again, we have more photons available, so we can afford to go to a long distance without worrying about extended exposure times and motion problems that result from extended exposure times. Okay. Okay, I had mentioned, enough said for that. I had mentioned that the distant effect is given by the inverse square law. Here is the expression of the inverse square law. What it's telling us is that the intensity at one position in space is equal to what you started out at some other position, the initial intensity, but that's related to the final in terms of this ratio, the first distance divided by the second distance to the second power. That's your inverse square law. And I had given you a little expression if you wanted the mathematical manipulations over here to find out intensity finals or output finals compared to the input finals. It goes as a ratio of the MASs. It's directly proportional there. MAS final divided by MES initial, and then you have your KVP final over KVP initial. That would, remember, the voltage is squared for output purposes. And now if you also change distances, then you would have, let me get this out of the way, then you would have that D1 over D2 problem. And since it's an inverse square law, you have the final in the denominator and you have the initial in the numerator. So if you wanted to make an expression or a calculation where you've changed all three things. You change the MAS, you change the voltage, and you change the distance. Just go down the line and have a running multiplication of the various parameters. Notice that the MAS variation is directly proportional, and voltage is proportional to square, and then you have the inverse square law for your distance effects. Here's an example. If the original output was 10 MR per MAS at 50 kV and 50 MAS at 1 meter, what's the new output if instead of 50 kV, you go to 100 kV? Instead of 50 MAS, you go to 100 MAS. Notice there you double. Notice that the voltages are double. And then instead of 1 meter, you go to 2 meters. Well, set up that running multiplication, and the final output is equal to the initial output, and there is the ratio of MASs. Here's the ratios of voltages. Notice it's squared, and then you went from 1 meter, the first distance, to the second distance, 2 meters squared. In reality, you don't even have to do this math. You can do it in your head. But following through the math, you come up with your 20 millisieverts per 100 MAS at 2 meters. Let me check something here. Okay, the original output was 10 MR per MAS, but now with these changes that we just went through, now you have 20 millisieverts per 100 MAS. 10 MR per MAS. Direct proportionality, you went from 50 to 100, so that's doubled. And then you went from, that's the problem. The KVP comes in as a square. So you went from 50 to 100, so that's 100 over 50 squared. That's a factor of 4. Okay, there's a factor of 4. Here's the actual math over here. There's a factor of 4 there. There is a factor of 2 for the MAS, and you went you went 1/4. You double the distance, so you get to 1/4 the exposure. So you end up with a net factor of 2, and you start out with 10, so you end up with 20. Wanted to make sure that my math was correct. So summarizing all of this, Emax is changed only by the voltage. Characteristic radiation is only changed by atomic number. The effective energy is changed by the voltages. You know, that's the energy. So your voltages come in, the filtration comes in, the electrical phase comes in, and then the output is changed by, as we've seen now, the MAS, the voltage, the filtration, and the phase and the distance. Oops, went a little too fast there. Okay. Okay, I want to move on now. That closes the discussion on the technique factors, and in fact, it closes the discussion on all of the X-ray production. Now we're going to go to the second part of the presentation, which says, how about the heat that's produced? Remember early on we mentioned that most of the heat, most of the kinetic energy that the electrons are carrying go into the production of heat. Look at the difference in fractions here. 99.5% of all the energy, greater than that in many cases, goes into heat. If you don't control that heat, you're going to blow up the tube. You're going to damage that tube. Tubes, X-ray tubes are very, very expensive. You don't want to blow up your tubes. And by the way, there's no possibility of a problem in the room if a tube does blow up. If it does blow up, it's all internal, so there's actually no consequences to the personnel walking around the room. But you do want to eliminate or minimize the possibility of exploding the tube, which now begs the question, how do we do that? What are the mechanisms of heat dissipation? What can we do to control and dissipate that heat? Okay, let's look at some terminology that I'll be using. I'll be using the word heat load. The heat load is a measure of how much heat you loaded on the anode of the tube. how much energy was deposited. Remember, energy and heat are, for our purposes, totally equivalent. And if you give a certain amount of heat to a tube, the next question is, how much can a tube take? What is the heat capacity of any given tube? The maximum heat load capacity of the tube. And the units that we use is called the heat unit. It's approximately, though not exactly equal, but it's approximately, for our purposes, the same unit of energy that we've been talking about all along, the joule. Okay? And how do you calculate how much heat is deposited at an anode? Well, it's very simple. It's just a simple product of the three parameters, kBp times Ma times time. Okay, and here's another variation on that same idea, and that is, what if I have a rapid serial acquisition of images, a very common in interventional radiology, where you would set up an algorithm where you would take so many per second for so many seconds, followed by so many per second for another set of seconds. And in other words, you're not just taking single exposures, you're taking rapid multiple exposures. When you do that, it's as if you had a very long exposure. Usually the exposure times are very short between exposures, so that it's as if you took one long exposure. So the way you handle that is you just throw in how many images that you take in that rapid sequence. So multiply the heat units with that parameter n, the number of images that you have just acquired. And then the other variation on this is that if you have three-phase units, produce more energy for the same voltage of the same MAS. How do you take that one into account? That's a fixed coefficient for three-phase 6-pulse, and I'll be talking about in the next chapter the electrical generation, and we'll talk more about three-phase. But given three-phase, and there's one form of three-phase which we call 6-pulse, you would have to increase the heat units by this parameter 1.35. That takes into account the added efficiency of producing heat that's true for three-phase. If you have three-phase 12-pulse and the so-called high-frequency generators, which we'll also talk about in the next chapter when we talk about generators in general, you need this coefficient 1.44, a little bit higher than if we had just 6-pulse. Okay. Let's talk a little introduction to three-phase over here and the heat problem. Remember, this whole discussion is centered around heat, how to control heat, how to specify it, where does the heat come from, etc. Here is your standard a standard single-phase waveform, okay? And you know that we talk about a kBp, the peak voltage that we're going to be operating at, and that is equal to Emax, the maximum energy. Okay, that's single phase. And you have an average energy that would appear somewhere between 0 and the maximum. I've drawn that in. Now, what if you had three-phase? The unique feature of three-phase is that the voltage does not go to 0. That's the whole idea of three-phase. The voltage does not go to 0. When you have voltages going to 0, what does that mean? You have no output. So in the single phase, where this consistently keeps going to 0, and even if it's not at 0, it spends a lot of time at low voltages. Low voltages are a problem. Low voltages mean that your outputs are very low. It means that the photons are very easily absorbed in the patient. The dose is high. So we go to three-phase, and we'll talk more about the features of this later on. But here is given the typical three-phase distribution. Doesn't go to 0. And again, you can talk about the peak voltage. So both of these could very well have the same peak voltage. But notice the difference in the average energy. Okay, the average voltage. Because this never goes to 0, because the variations are consistently closer to the maximum, your average energy is higher. But if average energy is higher, then you're going to have more heat being produced. So there's that justification for those little coefficients for three-phase, that 1.35 and that 1.44 that we had mentioned. Okay, that's also true for high-frequency units. They are also giving you a higher average energy. Energy is closer to the peak energies when we do three-phase and when we do high-frequency generators. So now let's get down to brass tacks. What could we do to keep the heat down as much as possible? I developed a whole series of bullet points. The first bullet point is warm up. Warm the tube up. What's that all about? Imagine or visualize in a typical hospital that relatively cold, air conditioning going on all the time, and no one has used the x-ray machine all night long, and the techs come in and they're ready for the first patient in the morning. The anode is very cold, or at least, it's room temperature. And the first patient is a big old heavy patient. Well, a big old heavy patient means that you got to go to high KVs, you got to go to a large MAS. In other words, you're going to put a big heat load on the target. There's the problem. When you have a relatively cold target and you have to expose that target to a high heat load, then you're going to have a very sudden deposition of heat. Depending on how short an exposure time you're going to use, a sudden deposition of heat, and now which produces a sudden expansion of metal at the point at which you deposited the heat. And now what happens? That expansion of metal expands against the cold parts of the anode, and now you got a problem. Expanding metal up against a cold metal that doesn't want to expand, you can crack the anode. And if you crack the anode, it releases oxygen from within the anode. All metals have oxygen inside. And once you break open and make holes or cracks in the target, out comes oxygen. Not very much, but you're going to get oxygen coming out. Oxygen will serve to oxidize the filament, and pop goes the filament. You just blew up the tube. So the first dissipation mechanism, this tube warm-up, all you do is just make a very long, low kV exposure. Low MA, low kV exposure, but relatively long time. That means that then you will, since it's a long exposure, you're going to have electrons hitting over the whole periphery of the target, and but it's a very low heat load for any given point on the target, and you're warming up the tube so that when you take a bread and butter exposure, especially on a large patient, you don't blow up the tube. So tube warm up. Here's another heat dissipation mechanism. By the way, on the tube warm up, I've noticed these days we buy tubes that have relatively high heat capacities, so you don't see techs warming up tubes very often. The only times they would warm it up very often if they happen to have tubes that have very small focal spots. That small focal spots means that the heat load is concentrated in an even smaller spot, so that you're more at risk for building up to the point where you have a meltdown. Well, the second mechanism is an oil bath. All of our X-ray tubes, from mammography to CT, all of them have oil baths. What does the oil bath do? Notice we have the X-ray tube, usually a glass envelope X-ray tube containing the anode and the filament, and then you have your outside metal housing. And the idea here is that you fill that space with oil. Why? Well, oil has a very high specific heat, which means that it absorbs the heat from the target. It's actually radiative heat, as given by these red arrows over here. It absorbs that radiative heat, and since it has a high specific heat capacity, what that means is that it absorbs a lot of heat without itself rising in temperature. And if it doesn't rise in temperature significantly, that means it maintains a temperature differential between the target and the oil. And and I'm sure you remember from physical chemistry that the flow of heat goes depending on the difference in temperatures between one region of space and another region of space. So oil that completely bathes the glass envelope, it's over this whole region here, serves as a very efficient mechanism of very efficiently removing the heat from the target that's being radiated from the target, and very important source of heat dissipation. And we take that one step further with CT scanners. Do realize that CT scanners are the one modality that produces the greatest amount of heat. Okay. Remember that in CT scanning, you're spiraling around the patient, so you have relatively long exposure times, and all CT scanning is done at very high voltages. The very highest voltages that are used in radiology are in CT scanning. So there's in general, the heat loads are very, very high, the highest in all of radiology. So we do this additional step where we will pump the oil, hot oil, out of the oil bath through a heat exchanger, and then pump it back into the oil bath. But now it's cooled off as it goes through the heat exchanger. It cools off, so you're constantly trying to reduce the temperature of the oil. And here we go again. The lower the temperature of the oil, the more efficient the heat transfer from the anode to that oil. So it greatly enhances the heat capacity, and we need it in CT scanning. All CT scanners have that additional oil bath circulation system with heat exchangers. That we do not do that with interventional units, which is the next highest heat producing modality. And we certainly don't do it with standard radiography, fluoroscopy, and mammography. Only in CT scanning do we go that extra step with this mechanism. Here's another heat dissipation mechanism. Let's just have a fan blowing air across the tube. And here is, in fact, this image came right from your own department, and your X-ray tube over here, and then you have the fan it's just a simple fan that just blows air across the housing and presumably serves to cool off the oil bath. It's another mechanism of heat dissipation, and in this case, you're circulating air over the housing. Pretty much all of our systems, with the exception of, let's say, portable units that are relatively small packages and relatively simple units, but all stationary units pretty much have a fan to enhance the heat dissipation properties of that system. Here's another mechanism, and that is we use dual focal spots. Dual focal spots. That means that every tube has a choice. You can either use a small focal spot or you can use a large focal spot. How does that help us? Well, let's look at the small focal spot first. If you have a small focal spot, that means that you're concentrating the energy over a very small region. Well, if you concentrate the energy in a small region, you have a better chance of a meltdown in that particular region because you're concentrating the energy in a very small area. So you would have a small heat capacity. Well, that's a negative. Why would you want to use a small focal spot? Because of your resolution advantage. Your spatial resolution image quality improves for small focal spots. So it behooves you to use the small focal spots as often as possible with as many patients as possible to cash in on spatial resolution. When can you use the small focal spots? When you don't have to impress a big heat load on the tube. If you have a very thin patient, if you're doing extremities, if you're doing a wrist, for instance, where it doesn't take very much a radiation to penetrate a relatively thin cross-section, well, then that means that you're not going to impress that much of a heat load on the target, so it can withstand your choice of a small focal spot. So thinner is where and less dense is where you would use the small focal spots to capitalize on spatial resolution. Well, if spatial resolution is so good for small focal spots, why would we want to go to large focal spots? See, large focal spots will give us poorer resolution. Oh, that's bad. But if you have a large patient and thicker cross sections that you have to penetrate and denser regions of the patient that you have to penetrate, that means up goes the kV, up goes the MA, up goes the exposure times, and up goes the heat load. And now the large focal spots are capable of withstanding greater heat loads. It has a greater heat capacity. So what we have here is a tug of war. You want the spatial resolution, but you don't want to blow up the tube. So depending on the patient and the needs of the patient, the thickness of the patient, density, etc., you have to make a wise choice. Actually, this is so significant. The possibility of blowing a tube up is so possible that all of our X-ray tubes have built-in controls, so that the engineers build in a governor into the system. So if the tech sets up a particular technique, the system knows that that technique is too much, and it'll give you a raspberry. It won't expose for you, and you got to then go searching for a combination of techniques, or go to a larger focal spots, or a combination of techniques where the machine will allow the exposure for you. So you do have that built-in control, and thank goodness for it, because many times you would take the wrong settings and blow up a tube. Okay, so here is a summary of what we're saying. The choice of focal spot sizes is going to depend on the spatial resolution that you would like versus the heat capacity of the system. There's a good and the bad. You want to go as small as possible to capitalize on the good spatial resolution, but you can't go too small because you blow up the tube, the heat capacity of the system. And so here is going in the opposite direction. It's the same thing, but going in the opposite direction. Okay, now, very common board question that just brings this all to bear in a real world situation. You have a patient and you're going to take a radiograph of a wrist. What focal spot should you use and why? Well, I already gave you the answer to that. A wrist is relatively thin. You want to go to a small focal spot. Why? So that you can get better resolution. And the rationale being small body parts require a lower KV, lower MAS. That results in lower heat loads, so you can get away with a smaller focal spot. Very common question, and it's sort of a no-brainer. Very easy to work out. Here are some pictures of what we're talking about. Here is a large on the focal spot. It's this coil of wire that you see here on the left side, and that's the large one. Its physical dimensions are actually larger, as you see over here. And then the small is on the right. You can see the physical dimensions are on the right. Are smaller, and they are in sort of a indentation, like a little valley. You have these protrusions on the either side. Those are the focusing cups. Remember we mentioned that the electrons coming off of these coils, these little helical filaments, the electrons coming off of them go off in every which way direction, and you want to focus them to a small focal spot at the target. How do you do that? With the focusing cup. It's just like a little valley, and with these protrusions sticking out that help you focus these electrons. You put a voltage on these, a negative voltage that will pinch the electrons coming from the filament down to a point, a focus point. Typical sizes, do take these numbers home with you. They have been asked on the boards, primarily in the mammo case. Notice how small the mammo focal spots are, 0.1 millimeters. You can hardly see that, but that's what we have. That's for the small, and for the large, 0.3. In radiography, and that would also be true for fluoroscopy and CT scanning, you have a significantly bigger focal spots. How come? Well, in radiography, you got full patients. You got to go through abdomens and lateral pelvises and skulls with bone, and you need voltages and MASs. So you got to have larger focal spots in general. So even the small is relatively large in radiography, CT, and fluoro. In mammo, you're always going through a relatively thin patient. Even for large breasts, it's still relatively thin compared to full cross-section patients. Okay, here's a bigger view of that of the cathode filament structure. As we just showed, you have your filaments down here, small and large focal spots, but then this is connected to the cathode structure, which then is connected to the electrical supply that feeds the system. Okay, here is another heat dissipation mechanism. Again, this one is utilized by all of our modalities. Again, a major source of heat dissipation, and that's rotating the anode. Rotating the anode. Up till now, I've been describing the X-ray production process by just stating the electrons impinge on a point. Okay, but now we're going to add another little wrinkle to this. What if that point is rotating, or at least putting it this way, what if that point is rotating underneath the electron beam? What if you get a target that is spread out over the whole periphery of what we refer to as the anode disk, and then have this whole configuration rotating? So now what we have is the electrons coming from a fixed position, the filaments, hitting the target at a fixed point in space. Oops, come on. A fixed point in space, but the target, the metal itself, is rotating around. So now what you have is that now the electrons can impact a much larger region of metal. You're spreading the energy out over a larger region, and if you spread out the energy over a larger region, no one point of the target gets the full blast of heat. You got better heat capacity, and you still maintain a small focal spot. The size of the electron stream is still small or large, depending on which you chose, which size you chose, but it's still relatively small. So isn't this neat? Your focal spot size stays constant, but the metal under which over which the electrons deposit their energy keeps changing, so that you greatly expand your heat capacity of the system. The target area is the whole periphery of the anode disk. Looking at it from the other view, head on or face on, here is the region that you are going to bombard with the electrons. That size stays constant, but now the metal, which is rotating underneath it, is constantly changing, and you just spread out the energy that much more efficiently over the periphery of the rotor. This is what it looks like. Here is the anode disk, and here is the region where presumably you would have the electrons impinge. Let's look at this region over here. I can see that region relatively clearly on my computer screen. I'm not quite sure how good your overhead projection system is, but you can see the whole region. It's a pitted region. It goes, I'll show you over here, it goes from this point to this point. And it's a pitted region, and the normal wear and tear on targets is that you have a progressive pitting of the anode. That's perfectly normal, and as time goes on, you produce more and more pits. As you produce more and more pits, which are really point vaporizations of the tungsten, you do have a gradual release of oxygen, and remember, when you release oxygen, eventually pop goes the filament from oxidation damage. Talking about damage, look at the bottom of this. See this whitish area? This is evidently a damage, a region where there was more heat load than what the system could take, and you bore into, and you made into the tungsten, which then released oxygen and the eventual loss of that tube. I wouldn't be surprised if the reason you're looking at this is that you had a tube that imploded, or that got damaged, and they had to, they just salvaged this rotating anode from that damaged tube. That damage could have very well been as small as this. Just showing you where the X-rays come out. Okay, put it all together. Here is your cathode structure on the right. Your filaments are in that little indentation, little valley there underneath the focusing cup. And then here is your rotating anode. The electrons come out of the cathode structure and bombard the anode, and out goes the X-rays. This is the shaft back here that holds this anode in place. And this structure back here is if you're rotating something, you invariably need ball bearings to have a nice smooth rotational configuration. So your ball bearings are back over here. And there's coils in here so that you have an induction motor that gets this to rotate, and as we've seen then, you have a rotating anode. Now, if you have a rotating anode, there is we've said that a rotating anode can increase your heat capacity, but now we break it down with these two parameters. How big is the disk? Remember, the larger the disk, the bigger the periphery over which you are spreading out the energy. So your heat capacity goes up as your disk diameter goes up. And how about how fast is it moving? The faster it moves, the quicker you bring to bear fresh metal. The quicker you take out from under the electron bombardment the metal, so that you don't build up too much energy at any one point. So those are the two parameters associated with this idea of rotating anodes. And what is the result as far as the heat capacity? Let's look at that. Here's the anode disk diameter. Here's a given diameter. This is a relatively small diameter, the way I've drawn it. And there's your track, and there's your rotational direction. And now let's go to a larger diameter. Obviously, the periphery is going to be larger. And as we've just said, the larger the diameter of the periphery, of the rotating anode disk, the bigger the periphery, and the more you get to spread the energy over more metal, and you get more heat capacity. Okay. And how about disk velocity? How fast is it going? Here I made a calculation telling you, or calculating out a typical speed, a rotational speed. We usually work off of the line, the electrical supply that comes into the house, which is 60 cycles per second. That's 60 hertz. 60 cycles per second is 3,600 cycles per minute. Just multiply by 60, there's 60 seconds in a minute. Now, every time you have a cycle, you have one full rotation of the disk. So if you have 3,600 cycles per minute, that really translates to 3,600 rotations per minute. So your standard velocity is 3,600 RPM, but there's always some slippage. You don't get the exact 3,600. So we usually specify it at 3,400 RPM. There's your standard being single phase. Now, when we go to three-phase, you can triple up on that. Tripling up on that actually would give you 10,800 RPM, right? In other words, you would have 3 times your 60 or 180 cycles per second, and that works out to 10,800 rotations per minute. And again, you have slippage, and again, we specify it at a little bit lower value, 10,000 RPM, typical for three-phase. Okay. Notice that three-phase is going to give us a heat capacity advantage. Because it rotates faster, it moves the metal that much quicker out of the electron stream and out of the electron bombardment and the deposition of heat. Okay, so a three-phase will give you better heat capacity as well. Okay, now we've been talking about these rotating anodes, and there's a little wrinkle to this. When you configure these rotating anodes, there are two types that are available in the market. You have a fixed angle anode, and you have a biangular configuration. Okay, when you have a biangular, that means that you have two separate tracks, one for the small or one for the large. there's actually two angles involved, giving you two different tracks. I'm going to give you a picture of that presently. The opposite of that is just a fixed angle, where the electrons always hit the same region. But now, if you want a small focal spot, the small focal spot is just a smaller region of the large focal spot. So you bombard a region that you would also normally bombard with a large focal spot. Let's take a look at what we mean by all of that. Here's your fixed angle. There's your large focal spot. And then the small focal spot is just a region within that large focal spot. It's smaller, but typically it's confined to the overall size of the focal spot. And this would be for a fixed angle. And here is a breakdown of a biangular tube. Notice that you can detect two angles here. Here is one angle, and notice that this one is a little steeper. And it turns out that if it's a little steeper, you can get a smaller size. And you can see here the smaller focal spot projected toward the patient, and here you see a larger focal spot projected to the patient. So when you choose a small or a large, the system knows to focus the electrons either onto the small focal spot track or the large focal spot track, depending on what you have chosen. That's your biangular system. Now, here's a stationary anode. We don't use stationary anodes in any area of radiology. In the old days, we used a stationary anode for mammography. But all of our modalities now use rotating anodes. The advantage of heat dissipation is so great. All of our systems use rotating anodes. I just showed this image just to show you what a stationary anode would look like. The only place that you will find stationary anodes is not in diagnostic imaging. It's more in radiation oncology for radiation therapy. And what you see here also illustrates a heat dissipation mechanism. Copper. The actual focal spot is this round circle here, and the copper completely surrounds it. And copper is a great heat conductor. So as you produce the heat at the target, it's conducted away. This whole configuration is copper over here. Okay. Notice also that the angle is relatively large. It's closer to 45 degrees. Your focal spot size is not important in therapy. What's important is the uniformity of the X-ray beam. And we're going to be talking about the non-uniformity of X-ray beams a little bit later on in this chapter that we use in diagnostic imaging. Yeah, our diagnostic imaging, because we have small angles, we have we have beam non-uniformity. We're going to talk about that one. But in terms of this therapy type tubes, I'm illustrating number one. It's heat dissipation, the way we handle the heat dissipation there, and with this copper conducting, copper conducting system, and then just the fact that it has a very large focal spot, which is opposite of our needs in imaging. We want a small focal spot, but we want a small focal spot for image quality. But image quality is not important when you're treating a tumor. What you want is a uniform radiation dose to the full tumor. You don't want any beam uniformities. Well, moving on. Here's another mechanism of heat dissipation. Use carbon-backed anodes. Here is your regular anode that we've been talking about, and then we have a carbon backing to that anode where we blend or bind carbon directly to this the metal anode disc. What does that do for us? Carbon, it has a very high specific heat. It absorbs a lot of energy, but does not go up in temperature. So now we have another heat sink. I'd already talked about the oil bath that absorbs radiative heat. Oh, it looks like our time is just about up. Let me summarize this and then let you cut you guys loose. We had mentioned the oil bath as being a heat sink that absorbs a lot of heat because of its high specific heat, but the carbon also has a high specific heat, and because it is totally in contact with the anode, Now you conduct heat out of the anode disk to the carbon. The carbon is a heat sink. We're going to pick this up at the next time, but I just wanted to show you what it looks like before I leave. There is that carbon back anode, and here is the actual target. We'll pick it up again at this with this slide the next time we see each other. Are there any questions before we cut you loose? Okay, let's stop there and we'll pick it up again next time.